So we have defined a domain in this form omega. Such domain we say it is a simple domain, simple. Okay, and which the orientation we just talk about, so-called positive orientation. And of course, you can switch the order of x and y. You can, in our description of this omega, we use the x as the independent variable and the y to be the dependent variable, so that we have two functions, y equal to phi plus x and y equal to phi minus x. You can also switch the role of these two variables, so that you can consider the domain of this form. So this is C minus, this is C plus. So these two curves are function x equal psi plus y. This is x, this is y, and this curve is x equal psi minus y. So these two curves, this is x equal to psi minus y, and this curve is the graph of x equal psi plus y. Then they also bound, if psi minus is always no greater than psi plus, then these two curves also bound a domain in the xy plane, maybe with some horizontal part. So this domain is also a simple domain. But the orientation is also given anti-clockwise. That is, it is oriented here, 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 and here. Okay. So this is the orientation of a simple domain. Now, for simple domain, we have the following result. We consider the domain in this form, in the first form. Okay. So we state this as a lemma. Let P be a continuum. Here omega is the domain described here. Okay, omega is such a domain. And the partial derivative of P with respect to y is defined over omega. This is continuous and bounded. Then we have the following result. The integral of the partial derivative over the domain omega equal minus the integral of P dx. Here this omega is I have the better erase this one and draw our correct one. The omega is the domain that we just described in the last page, determined by two functions, phi plus and phi minus. This is a minus, this is a plus. Okay, so the boundary is oriented in this way. This is our omega. So it is easy to see that maybe I will write the omega explicitly. Assume omega is of this form. Okay, this is our omega. And the boundary we know that consists of four parts. These four parts we label them by some letter. So the boundary of omega consists of gamma plus minus and c plus minus. Gamma plus minus is the vertical boundary. So this is gamma plus, this is gamma minus. And the c plus and the c minus is the graph of phi plus and phi minus. This is c plus, this is c minus. C plus is the graph of y equal phi plus x. C minus is y equal phi minus x. Okay. So first, you will know that gamma plus minus p dx. What's this? Intuitively, along gamma plus or gamma minus, x is fixed. X is no change, only y change. Therefore, dx is 0. So this integral should be 0. Okay? Intuitively, this should be 0. But can you know why this is really 0? The proof is not difficult. Such an integral, you can use a parametrization of the curve. For example, gamma plus is the curve. Map t to the x coordinate of point in gamma plus is phi plus, and the point is t, where t runs in the interval phi minus a, phi plus a. Okay, so this map is orientation. Is a parametrization of the gamma plus. This map is the is a parametrization of our gamma plus, and which the given orientation, that is from go up along gamma plus. So by the computation of integral of this form, this is a special form of the flow integral we introduced when we study the line integral. Okay, by the computation of this integral, we know that gamma plus pxy dx equal phi minus a, phi plus a, p. You substituting the parametrization into this integral. So the parametrization is x equal to a plus, y equal to t. So x is a plus. So use a plus, y is t. Then dx is x prime t dt. But in this case, xt is identically a plus. Therefore, the derivative is 0. So this integral is 0. So this proves our claim that this is 0. Okay, very simple. Just by the computation of the flux integral. Flow integral. Okay, so so having this observation, we compute the double integral in the formula in the conclusion of the lemma. So the double integral we can, you want to compute the double integral over the domain omega, you can use the Fubini theorem to write this, to integrate with respect to y first and then x. With respect to y, the x is go from a minus to a plus. Then the y given an x in the interval a minus and a plus, the range of y is the y coordinate of the lower boundary to the y coordinate of the upper boundary. But the lower the point in the corresponding to the x on the lower boundary is phi minus x, and the upper boundary is phi plus x. So the range of the inner integral is phi minus x, phi plus x. Then Okay. Now this by the fundamental theorem of calculus, this definite integral, because the integral is the derivative of p. We consider x as a constant. Consider dp dy as a function of t of y. So by the fundamental theorem of algebra, of calculus, we copy this. But the inner integral is p, x is fixed, but the y should be replaced by the limit, upper limit and the lower limit of the integral. Okay. Now we consider the first term. What's the first term? The first term is precisely the integral over the upper boundary. Pxy dx. Okay, as you can check, because the integral of pxy, we can parametrize the c plus by x, using x as a parameter, then x phi plus x. Then let's see, has a minus sign here. I have no space to write in this page. Maybe I should go to the next page. Okay, I go to the next page. So we should compute the c plus pxy dx. This we take the parametrization of c plus, that is t to the t phi plus t, where t goes from a minus a plus. Then by the computation formula for floor integral, this is precisely, this will equal a minus a plus. If this is denoted by gamma, p xt yt dx is x prime t dt. Okay, dx is x prime t dt. So this is xt is t by the parameterization. Xt is t, therefore x prime t is precisely x. Okay, so this is a plus, a minus a plus p t pt yt is phi plus t, then dt, right? So this is precisely a minus a plus px phi plus x dx, because this is simply changing, using another letter to denote the integral variable. This does not affect the value of the integral. So we have this. This definite integral is precisely the floor integral of p. But our c plus, here the c plus, in this computation, the c plus is this direction, because corresponding to x increasing. So this the orientation of this computation for the c plus is not the same as in our lemma, because in our lemma, for our c plus, we use the orientation indicated by the red arrow, from right to left. So we need to add a minus sign for this integral. Okay. So the first term we already know. The first term is a minus sign, which is a minus sign, the integral over the curve say plus. Now for the second term is px phi minus, that is the lower boundary. The computation is similar to the upper boundary, but the difference is that for the lower boundary, when x increasing from a minus to a plus, the corresponding orientation for the curve say minus is coincide with our required orientation. So we don't need to add a minus sign in front of the integral, but we already have a minus sign here. Okay, we already have a minus sign, so we will copy the minus sign. This minus sign is this minus sign, not from our computation. So the minus sign is here. That is our already have in the expression. Therefore, we just copy it here. But for the first term, we do not have a minus sign. But we need a minus sign here because the orientation reason. Okay, so this is say minus pxy dx. But the boundary of omega consists of 4 parts, maybe 2 or maybe 3, because one or both of the vertical part might be linked to a single point. Okay, in that case, we do not have a vertical part or only have one vertical part, but at most we have 2 vertical parts, gamma plus and gamma minus. But the integral over the vertical part is 0, as we explained before. But for the curve part, that is the C plus and C minus. So the sum of these 2 parts is just the integral over the boundary of omega. Okay, so this is pxy dx, and we have a minus sign. We have a minus sign. Minus sign comes from here. Okay, these two give us the minus sign. The boundary consists of 4 parts. In addition to C plus and C minus, we also have gamma plus and gamma minus. But the gamma part, the integral along the gamma part is 0. Therefore, the integral over C plus and C minus, the sum of the integral over C plus and C minus equal the integral over the whole boundary. So this proves our lemma. Okay.